Hello, 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 everybody, and welcome back. Welcome back to more of the 11th grade level contest, the written contest Hypatia. And we are on question number 4 from the 2010 Hypatia. Okay. So, question number 4, we've got 3 parts here. And looks like it's just some basic equations. Usually on a part 4, they introduce some brand new concept like a Franklin list is blah, or a Jeffreys rearrangement, or the Markov numbers, but we don't have any of that. It looks like just some basic solving of equations, so we'll see if that's true. Determine all real values of x satisfying the equation x to the 4 minus 6x squared plus 8 equals 0. Okay. All real values of x, so we're not just looking for integers or rationals or things like that. Now, you might be thrown off a bit. If you've never seen a question like this, they do pop up. But you might say to yourself, well, it's x to the 4. I don't know how to solve it when there's x to the 4. Okay? Now, I've seen people say, I know my math. I learned it. You can only solve the x squared stuff. Quadratic formula. And yes, that's true, and that's the one that you know a whole lot. But you can actually solve things with powers of 4 and powers of 3 in the x's, cubics and quartic equations there. And there are formulas for them. They're just so complicated, no one would reasonably expect you to memorize them. Okay, I think I have them written down somewhere, but that was just out of sheer curiosity. But there's a trick to ones like this, because notice it's x to the 4, x squared, and then no x's at all. There's no single x. There's no single x squared. So if you haven't seen this before, it's a nice little trick. We're going to give a new variable name. Okay, we do have to write everything down, so let's be nice and neat and say let y equal x squared. And x to the 4, I think it was minus 6x squared plus 8 equals 0. I think that was it. Let's just double check. Yep, minus 6. So then this becomes, well, x squared is what x to the 4 is. So this is just y squared minus 6y plus 8. We breathe a sigh of relief because now we are in more familiar territory. It's quadratic. And so you can use the quadratic formula, or you could factor it. You'll get a minus 4 and a minus 8. Two numbers that multiply to 8 add to negative 6. You're going to have minus 4 and minus 2. So this tells me y is equal to 4 or y is equal to 2. But we're not done there. We wanted real values of x. So we've got x squared is equal to 4 or x squared is equal to 2. So x being plus or minus 2 or plus or minus the square root of 2. That's the best way we can write that. Satisfy the equation. Okay. As an added little fun side note, we have no more than 4 for any solution to a quartic. No more than 4 different solutions. You might have less in case a solution was doubled up or things like that. But yeah, there we go. That wasn't so bad for A part. And if you didn't know that little trick, it's a great one to use. Actually, I'll say a little bit more about it. It pops up in the weirdest places. I think I mentioned when I was doing question 1 or 2 that I recently did a Euclid with a group, and there was another Euclid a couple weeks ago, and it had an equation, I think, like this. And you might say, E. Well, actually, we'll make it not E. Just for those of us who haven't taken any sort of calculus or anything like that, or logarithms. We'll make it 3. Anyway, you might say, 3 to the whatever. I don't know how to do this. We can't solve this. The k value is up here. What am I to do? But if I let y equal 3k, well, suddenly 3 to the 2k, if we know our exponents, is 3 to the k squared, and this becomes y squared plus py plus q equals 0. So this technique pops up a whole lot. It's not just when you got x to the 4s. Okay? So be on the lookout. Be aware of it. And maybe we'll be using more of it as we move on. Now, let's get back to the question. 4b. Determine the smallest positive integer n So now we don't want real numbers, we want positive integers n, for which x to the 4 plus 2010 x squared plus n can be factored as x squared plus rx plus s, x squared plus tx plus u, with r, s, t, u integers, and r not equal to 0. Okay. So there's a lot of variables going on here. We want to solve for n. That's something we don't know. But we also got this r, s, t, and u. They're integers. We know r can't be 0. Okay, fine. We accept that. But what are we to do? Well, I would set up an equation. What equation would we set up? Well, we only really have one that we can talk about. Was it plus? It's got to be minus. No, it's plus this time. Cool. Plus n, and it was plus n, correct? Yeah. Well, this has got to be able to be factored like this. Okay, that's really the only equation we can set up. Everything else comes later. You know, r can't be 0 and so forth. But what we can do is we can expand this this right-hand side. You get x to the 4 plus tx to the 3 plus ux squared plus rx cubed plus rtx squared plus rux plus sx squared plus stx plus su. Okay. What I'm going to do is I am going to group my powers of my powers of x. So we'll get r plus t x cubed, and then plus s plus rt plus u x squared plus ru plus st x plus su. So the equation on the left-hand side has got to be equal to the equation on the right-hand side. So not too much of a problem. I mean, the x4, we got one of those. But notice that on the right-hand side, we don't have any x to the 3's, but we do have r plus tx to the 3's. So this is sort of a technique called comparing coefficients. Two polynomials can only be equal if their coefficients match in the same places. So the powers of 3 have the same thing in front. The powers of x to the 2 have the same thing in front. So this tells me, well, 1 times x to the 4 has got to be equal to 1 times x to the 4, but 0 has got to be equal to r plus t. 2010 has got to be equal to s plus rt plus u. 0, because there's no x's, has got to be equal to ru plus st, and n has to be written as su. Okay, so that's fine. Now, just before we move on, and there is some more interesting stuff we can say here, n has to be written as s times u. Well, what do we want to do? We want the smallest n. So we might start thinking of wanting small s's and small u's to make their product n small. Just thoughts, just thoughts. Anyway, this first equation here, 0 is equal to r plus t. We can rearrange that one pretty quickly. I'm going to copy these over for a moment. 0 is r plus t. 2010 is u plus rt, or sorry, s plus rt plus u. 0 is r, would be ru plus st, and n is going to have to be su. Right? I did copy those, right? Correct? Yeah, ru plus st. Okay. Now this first one tells me that t has got to be equal to negative r. Well, hey, I can put that into all my other equations. You know, s minus r squared plus u. And 0 is, I can take out a factor of r here. R u minus s. and n is, well, it's still SU. But now this equation, it can only be 0 if r is 0 or u minus s is 0. But r can't be 0. They told us that in the equation, or sorry, in the setup, in the question. So s has got to be equal to u. Okay. Okay. So s has got to be equal to u. Well, that tells me now that so we got some more simplification here. So s has got to be equal to u. So we'll call this 2s minus r squared. That is a minus sign, despite however much it looks like a plus sign. And n is now s squared. Okay. So just by comparing these coefficients, we have reduced it a whole lot. We now have x to the 4 plus 2010x squared plus n is equal to x squared plus rx plus s times x squared minus rx plus s. Now, I want to make n as small as possible. So n is as small as possible when s is as small as possible. Okay, so I want s here to be very small. So let's talk about. So you can bring the r squared over, and that's got to be equal to 2s. Okay. So both of these are positive, so s is going to have to be positive. Well, that's good, because if we could just get smaller and smaller... Actually, no, a really big negative s would still give us a big n there, so that's not particularly helpful. But we want to start looking... We really just need 2010 plus a square. A non-zero square is equal to an even number. Okay. Now, if r were 0, yeah, we could get s is 1005. Okay, but they said r can't be 0. So, just very quickly, this isn't going to take us too long, but we just need this to be even. Right? So if r is 1, well, we get 2011. So, not even. If r is 2, well, we get 2014. Let's add on 4. Okay, so therefore, the smallest 2s is going to be when r is 2, and s is going to be 1007. So our smallest n is 1007 squared, which is 1. It's going to end in a 49. There'll be a 0 here, a 1, 4, and I think a 0 there. No sense in doing that in my head. I can just grab my calculator and do it. 107 squared, 1014049. Hey, I'm feeling good. So this is my smallest n. Okay, pretty big actually, but it's the one that satisfies our constraint. If r is non-zero and it's an integer, well, the t that we chose is an integer. S and u have to be equal, so we've got integers there. And yeah, so that all works out. And if we wanted to, we could at least verify what we've got going on here by actually taking my r and my s and saying, well, does this actually work out? X squared plus 2x plus 107, x squared minus 2x plus 107. And most of this is going to be going just fine, but we'll get 107x squared plus 107x squared minus 4x. Well, that's 2014 minus 4. Yeah, that gets me the 2010. So, yeah, that all works out. Okay, so that's the smallest n that'll satisfy B there. Okay, So now we got C part here. Prove that x to the 4 plus mx squared plus n cannot be factored as in B. So like this, with integers and r not equal to 0, for any integers m and n, with n minus m equal to 37. Okay. So I'm going to start by saying, well, from B, I already know that from our work in B, which gave us a little bit of a head start, we know t is equal to negative r and u is equal to s. So we've got x to the 4 plus mx squared plus n is equal to x squared plus rx plus s, x squared minus rx plus s. N is going to have to be equal to s squared, and m is going to be 2s minus r squared. Okay. So that's our information, and we're basically just completely importing our work. We're just changing our 2010, which didn't come into play until the very end. We're just turning that into m. Okay? It's a nice little shortcut. If you're worried about that, if you're worried, wow, you didn't write a whole lot for your start of C, by all means, copy your expansion, your calculation. But remember, we only have so much time on these contests. And you are allowed to reference earlier parts of the question to make your life easier, to make your work a little shorter. Okay? So that's what we've done here. The difficulty in the question will likely not lie in the factoring and expanding out. They wouldn't make 4C like that. So now the challenge is m minus n is equal to 37. Okay, so n minus n is 37. No, it's n minus n. It's the wrong way around. Wrong way around. So n minus m is equal to 37. That makes sense, because what did we see? M was 2010, and n was a huge number. So plugging in our expressions, we get s squared minus 2s plus r squared is equal to 37. If we had an r here, we'd have an s plus s minus r squared, but we don't quite have that. But let's think. What do we have? Well, we can bring the 37 over, and we've got equal to 0. And maybe if I put these brackets around, it'll help people see that we've got a quadratic in terms of s. By the quadratic formula, we know s is negative b plus or minus the square root of b squared minus 4a, which is 1, c, which is r squared, minus 37, all over 2a. So we can divide by 2 on top and bottom. We're going to have to, the 2 becomes a 4 here, so we're going to have to, it becomes square root of 1 minus r squared minus 37. Okay. So now we can, s is equal to 1 plus or minus square root of 1 minus negative 37 is 38, and then minus r squared. Okay. Yeah, 38 and then r squared. Okay. So, what do we need here? Well, for s to be an integer, we need root 38 minus r squared to be an integer. And I'm betting that just won't happen. Okay, so we need 38 minus r squared to be a perfect square. Well, 38 isn't involved in any Pythagorean triples. Or you could, make a chart. R, really you only need to go, well, you can't have r as 0, so we'll start with 1. I guess you could start with -6 if you wanted, because there's nothing that says r can't be a positive integer. So we need 38 minus r squared to be a perfect square. 38 minus r squared is equal to some k squared. And we can see that k squared is going to have to be between 0 and 38. So k is going to have to be between 0 and 6. So now let's get k. We'll get 38 minus k squared is equal to r squared. And then r an integer. Because as long as this equation is, as long as we pick an appropriate k, we're going to get s. S will be 1 plus or minus k. And that'd be fine. S would be an integer there. So we can get 0, 1, 2, 3, 4, 5, or 6. It's just a question of, is r an integer? And in each of these cases, no, r is not an integer. Okay, root 38. 38 is not a square. We'll get 37. Nope, that's not a square. 34. No. 29. 38 minus 9 is 29. No. 16. So that'll be 28 minus 6. That's 22. No. How about 25? No, that's 13. And finally 2. No, it's not going to work out. So no matter what k value, we see r is not an integer. So this tells me we cannot factor x to the 4 minus, it was plus, right? Yeah, plus, okay. If this had been a minus, then I would have had to go back and take another look, because it would actually be minus m was 2s minus r squared, and that might set things up differently. Got to reread these things. We got to read these things carefully. Anyway, we cannot factor this like we did in part B if n minus m is 37. Okay, and that's exactly what we were asked to show. And it's probably a range of values. 37 is probably the smallest one that works. But if we just go back and take a look, none of our analysis up until this equation right here is going to be a problem. The 2's will still factor out. So 37 is probably just a nice number. You'd have to do... So instead of 37, we could have, like, I don't know. This is just me thinking out loud now. 1 minus, and then we'd have r squared minus, we'll call it y, capital Y. You'll be able to rearrange 1 plus or minus, and then it'll be square root 1 plus y minus r squared. And if you're given a particular y, you'll get 1 plus y, and you just need to make sure that that's not part of a Pythagorean triple. And then to ensure that s is an integer, this thing's got to be a square, which it then can't be. 1 plus y can't be a sum of 2 squares. And so, 38, not a sum of 2 squares. It's got to be a sum of 4 squares, but that's different math altogether. And so there's lots of different y's we could take. Okay, so that's some nifty side math there. Okay, so the 37 isn't particularly unique here. All right, so for example, I think 7 would also work. So if y was 6, and then you'd have 1 plus y is 7. 7 is not a sum of 2 squares, so that also wouldn't work. But there we go. 37, n minus m being 37, not going to work. No factoring. It's actually a surprisingly easy C part, I think. Not particularly complaining, but it's nice. I thought everything in 4 there was quite straightforward, and I was expecting C to be harder than it was. Now, usually in Hypatia, 4C or 4D, depending on the last part of 4 is usually quite challenging, requires us to know a lot of theory, but really We just took our factorings and our knowledge from B part, applied it, and then set up the only equation we could, n minus m. I suppose there's a little difficulty there if you couldn't see, oh, it's a quadratic that we need to factor, but I'd say you were appropriately primed for that by 4a, recognizing a quadratic when you might not. Yeah, so good 2010 paper overall. You know, a little lighter than some of the other ones, especially in the 4 part, but that's okay. My next Hypatia will be the 2011. I hope to see you guys there, and you can, of course, click the second link in the description, go to the CEMC website, get all their past contests, and you can try the 2011 Hypatia before I've even got it posted. Or next up, I think, will be the 2010 Euclid, so by all means, stay tuned for that. Feel free to like or subscribe or any of that fun stuff. And, yeah, I got nothing else to say, so I will see you guys in a future video. So long, and have a wonderful day.